In this video, I'm going to show you how to represent and evaluate sets using set builder notation. For example, here we've got a set A which is given using set builder notation, and we want to find out what are the elements of A. First, let's talk about how to read the set builder notation. The key to reading set builder notation is to understand that the vertical line in the middle represents such that. So you can read this as A equals the set of elements n over n plus 1 such that n is in the set of all natural numbers. So the elements of A are really just all the numbers that can be expressed as n divided by n plus 1 such that n is a natural number, like 1, 2, 3, or so on. So really all we have to do is take this set of natural numbers, and for each number n in here, we have to plug it into the formula n divided by n plus 1. And those will give us our elements of A. So let's go ahead and write that down. So A equals the set of what? Well, first of all, the first element is going to be given by n equals 1. And plugging in n equals 1 into this formula here, we just have 1 over 1 plus 1. Okay, and then we'll simplify that later, but let's move on. So how about n equals 2? For n equals 2, we just plug that in, and we have 2 over 2 plus 1. Okay, continuing this for n equals 3, we've got 3 over 3 plus 1. Continuing this for n equals 4, we've got 4 over 4 plus 1. And then we'll just add some dots to indicate that we keep going on in this fashion. Okay, so let's just simplify what we've got here. So A is really equal to, well, 1 over 1 plus 1 is just a half. Then 2 over 2 plus 1 is just 2/3. Then 3 over 3 plus 1, 3/4. And then 4 over 4 plus 1, 4 over 5, and so on. So there we go. Great. Those are the elements of A. Alright, now we want to use set builder notation to describe this set 1, 3, 5, 7, 9. These are just the odd natural numbers up to 9. One thing to notice here is that these numbers are all spaced 2 apart. 1 plus 2 makes 3, then 3 plus 2 makes 5, then 5 plus 2 makes 7, then plus 2 is 9. So why don't we start off using the formula 2n, and then we'll tweak it as needed. 2n, where n is a natural number. So let's go ahead and compute this set first, and then we'll tweak the formula as needed to get it to represent this. Okay, so 2n where n is a natural number. So this is going to be 2 times 1, 2 times 2, 2 times 3, 2 times 4, and so on. So 2 times 1 is 2, then 2 times 2 is 4, then 2 times 3 is 6, then 2 times 4 is 8. Yeah, so this is just all the even numbers starting at 2. Okay, so we have two little things that are not right just yet. So first of all, this is starting at 2, but we should really be starting at 1. And second of all, this set contains infinitely many elements, whereas our set over here contains just 5 elements. Let's start by taking care of the 2. Let's turn that into a 1. And we also want to turn that 4 into a 3, the 6 into a 5, the 8 into the 7. Do you see a pattern here? But we really just want to subtract 1 from each element. So let's adjust our formula here. 2n, and let's subtract 1 from that. So write 2n minus 1 such that n is in the set of natural numbers. Alright, so that set then is going to be all of these elements minus 1. So 1, 3, 5, 7, 9, 11, just going on and on, 13, and so on. I've written a lot more entries so that we can see the problem here. This is infinitely many entries, and this is just 5 entries. So we really just want these entries here. So how can we restrict this set to just have these 5 entries? Well, we can pay attention to what is the number n that we're plugging in. This entry here, that's generated by n equals 1. this entry is generated by n equals 2, then the next one n equals 3, the next one n equals 4, and then the last one n equals 5. And that's where we want to stop. We want to stop when n equals 5. We don't want to let n get any bigger than 5, otherwise we get more elements that are not in the set here. So how we're going to do that is we're going to impose an additional constraint. Not only will n be in the set of natural numbers, but it will also have to be less than or equal to 5. 5 is going to be the upper limit for n here. So let's do that. So 2n minus 1 such that n is an element of the natural numbers, and also n is less than or equal to 5. There we go. So that's going to give us our n equals 1 is 1, n equals 2, plug that in, you get 3, n equals 3, plug that in, you get 5, n equals 4, plug that in, you get 7, n equals 5, plug that in, you get 9, and that's where we stop because we've got that condition now that n has to be less than or equal to 5. So there we go. That matches up with our set here. So that's the set builder notation that we'll use to describe the set. Here's another example. And in this example, we want to evaluate the set B. We're given its set builder notation. Okay, so if B is 5n such that n is in the set of integers, and n squared is less than 10, then what are the elements of B? So how should we start out here? Well, n is coming from the integers, so why don't we start out by listing the set of integers. The set of integers is just z, which is equal to, well, it goes on to negative infinity, then as you come back from negative infinity, you reach like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and you just keep going on and on. Okay, so that's the set of integers, and n's are the elements of this set. So like 1, that's n equals 1, 2, that's n equals 2, and so on. Now we have an additional constraint here. N squared has to be less than 10. So let's check all of these elements and only keep the ones that are less than 10. So below each of these elements here, let's write the squares. Let's write n squared. If these are n's, we'll write n squared below. So 0 squared is just 0, 1 squared is just 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Going the other way, -1 squared is 1, -2 squared is 4, -3 squared is 9, -4 squared 16, -5 squared is 25, and so on. Now let's remove all of the elements for which n squared is not less than 10. So looking here, oh, here's 16. 16 is not less than 10, so we really shouldn't have 4 as an n, because when we square it, it's not less than 10. Likewise, 5 isn't going to be less than 10 when we square it. We get 25, definitely not less than 10. As we increase n, the square just keeps getting bigger and bigger. So next one's going to be 36, then 49. So we don't want any of the numbers past 4, including 4. We don't want 4 or any higher numbers. It's the same situation on the negative side. We don't want -4 because 16 is not less than 10. We don't want -5, and the squares of the numbers are just going to keep getting bigger as the numbers get more negative and more negative. So we don't want those either. So all we want for our values of n are really just these values right here, because these values, when we square them, they are indeed less than 10. So let's write down our finding. Because we've adjusted this set, it's no longer just the set of integers. We've eliminated a whole lot of elements from it. Let's write down what we have. So what we have is the set of n such that n is in the set of integers and n squared is less than 10. We removed all the elements which don't satisfy this criteria. And the result is that we just have -3, -2, -1, 0, 1, 2, 3. Alright, so now the only difference here between this set in set builder notation and the set B is that B has 5n and we have just n in our set. So we need to create the set which has 5n, such that same conditions, n is an element of the integers and n squared is less than 10. So really we're just plugging in all these numbers into the formula 5n, and that's going to be the output results. So the bottom line is we just have to multiply each of these numbers by 5 to get that 5n formula in front here. So let's go ahead and do that. So negative 3 times 5 is just going to be negative 15. Negative 2 times 5 is negative 10. Negative 1 times 5 is negative 5. 0 times 5, 0. Then 1 times 5, 5. 2 times 5 is 10. And 3 times 5 is 15. And there we go. These are the elements of B then. Here's our final example, and this example is interesting because now we're going to be using coordinates instead of just numbers. So we want to use set builder notation to describe the coordinates of all the points contained by the triangle with vertices A, 0, 0, B, 2, 0, and C, 0, 4. That's this triangle right here. We've got A, B, and C, and we want to write the set which contains all of the points which are in the shaded region within the triangle. So where do we even begin? Well, a good way to start is by thinking about our points here. What kind of form do the points have? Well, the points are just of the form x, y. Okay, so we want points x, y, and such that what? What kind of points x, y do we want? Well, what are x and what are y from? Well, x and y are both from the set of real numbers. We can have any real number as a coordinate here. So we'll write x and y are in the set of real numbers. Okay, and then what else? What else do we want? Well, the main condition here is that x and y has to be in the triangle. So let's just write that down verbally. X, y is in the triangle. And we'll figure out how to write that more mathematically. So how are we going to write this mathematically? How do we say that the coordinate x, y is in the triangle? Well, we need to say something about x and we need to say something about y such that we force the point x, y to be in the triangle. Why don't we look at the point x first? So looking at x, what do we need from x? Well, all the points in the triangle have x coordinates between 0 and 2. So why don't we use that constraint? So x has to be between 0 and 2. That'll be our constraint here. 0 is less than x is less than 2. And that just comes from looking at the base of the triangle here. All of the x values in the triangle, as we see, are between 0 and 2. Okay, so now we need a condition on y. And this one's going to be a little bit tougher. But we're going to use this condition that we already created for x. We're going to use that in our condition for y to make it a little bit easier. So condition for y. What can we write as our condition for y? Well, looking at the y values, they range between 0 and 4. But it's not enough to say that the y values are between 0 and 4. Because what about, say, like this point here? That point there has an x value that's between 0 and 2, and it has a y value that's between 0 and 4, but it's not in the triangle. So we have to make sure that our y values are depending on our x values, because the y values, the range of possible y values is shrinking as x goes from 0 to 2. So really we need to figure out the y needs to be between 0 and the top of the line here. So for any point x, these are possible y values. So let's just write that down. 0 is less than or equal to y is less than or equal to the line. And we'll figure out what the line is and write that in mathematical form. So first of all, what is the equation for the line? Well, we've got 2 points on the line. We've got the point 0, 4, and we've got the point 2, 0. And we can compute the slope between these points. The slope is equal to The rise, well, the rise is just -4 because we dropped down 4. And the run is just 2 because we're going over 2 to the right in the positive direction. So slope is -4 over 2, which is equal to -2. And that tells us that the line is then y equals -2x plus b plus our y-intercept, which we already know is 4. So -2x plus 4. Okay, so that's what we can write in for our line. So 0 is less than or equal to y is less than or equal to -2x plus 4. And great, so that'll work. We can choose any x between 0 and 2, and then we just have to make sure that the y is between 0 and the top of the line, which depends on x. Great. So now we've got all our mathematical notation, and let's just write our set once more, nice and clean. So the final result is that the set is the set of coordinates x, y, such that x and y are elements of the real numbers, and also x and y, the coordinate xy is in the triangle, so that means x is between 0 and 2, and then y is between 0 and the line -2x plus 4. 0 is less than or equal to y is less than or equal to -2x plus 4. And there we go, we've got it. This set represents all those points inside of this triangle. Now that we've learned how to represent and evaluate sets, in the future we'll also learn about operations on sets, such as union, intersection, and difference.